Okay, chapter 3, titled Into Eternity. It is a riddle wrapped in a mystery inside an enigma, said by Winston Churchill. In its proudest moment, classical physics could look upon almost everything one can see with what was believed to be total comprehension. The universe was envisioned to be an infinite space containing objects, stars, planets, moons, and the things on them, all made of matter, which in turn consisted of the fundamental elements of nature. All the matter of the universe consists of the elements, their compounds, and mixtures of these compounds, whose properties result from the various combinations of the orderly elements. These things are the constituents of everything seen in nature: the hills in the distance, the stones underfoot, the dust of the air, and even our own organic bodies. Chemists have ordered the forms of matter. Biologists have classified the species on the land, in the air, and under the seas. Wallace and Darwin have laid down the principles that we use to understand our own origins and form. The heavens are filled with stars like our own sun, planets, and moons of planets that move like our Earth under the force of gravity according to the laws of motion. The motions of wheels and gears, the flight of birds, the sounds of songs, of whistles, all are understood in mechanics, acoustics, and thermodynamics, governing the cycles of work and the balances of energy expended and conserved. As a consequence, light was revealed to be waves of electromagnetic radiation oscillating and rippling a fluid called the ether, like waves on a pond that fills all space. Light consists of the stuff of the force fields that surround magnets and of the static electricity that makes garments cling, but set into waves of motion that alternate from a magnetic field in one direction to an electric field perpendicular to the magnetic field, both cycling back and forth as the wave moves away in yet a third direction. These electromagnetic forces, as light from the sun, as the glue between atoms holding molecules together, fueling chemical reactions, creating the warmth of our bodies, powering machines, and making the blaze seen in fire. These electromagnetic forces and the force of gravity on Earth and in space provided an explanation of how things move about us. Classical science had found its picture of reality: our bodies, the objects around us, the smallest things we see, and the furthest distant objects in the sky, all are the matter of that classical reality. Their structure, their changes and motions, are explained by the concept of Newton's laws, Maxwell's equations, and Darwin's evolution. At its pinnacle, classical science seemed to have within its reach a complete picture of reality built upon the ideas of material objects set on an infinite stage. By the end of the classical period of physics, it seemed that the whole world could be surveyed with full understanding, issuing from the principles governing the motion of bodies and the radiation of light. There was seemingly a complete body of knowledge explaining how everything worked and embracing every aspect of scientific thought. But then, in a span of a few years at the turn of the century, Jean Perrin showed that matter is not infinitely divisible, but rather is made of atoms. Rutherford showed these atoms to be made up almost totally of empty space. The heavens were pushed back to the remoteness of galaxies, islands of billions upon billions of stars, themselves but specks of light in the vastness of space. Einstein showed The relativity of matter, of space, of time, and even stranger, he, along with Max Planck, helped to show us the beginnings of quantum theory, which has danced the 19th century sense of reality as in a measured ballroom waltz through a looking glass into the 20th century's jitterbug of quantum jumps. It all happened so quickly that the mind has not yet quite grasped the new reality that science has found. The change in our picture of reality is nowhere so great as in our understanding of the atomic nature of matter. Just before the turn of the 20th century, scientists such as Wilhelm Ostwald, Ernst Mach, Pierre Duhem, Marcelin Berthelot, and even Max Planck, whose later discoveries would be the turning point for modern physics, had in one way or another taken a stand against what they believe to be a philosophical, preposterous hypothesis. The idea that matter could be divided into some smallest chemical constituents, divided into molecules and atoms. Many believe that the innermost structure of matter could be built up out of infinitely divisible electromagnetic fields. Others simply believe that any hypothesis about atoms, something that could not possibly be seen, must be foolishness. The conflict was sharpened by the rise, particularly in Vienna, of the philosophical doctrine called logical positivism, which sought to purge philosophy and science of concepts not supported by direct sensory experience. Strong passions animated these thinkers. The opposition to the atomistic theory was not merely fierce, it was vicious, and it chose as its victim the man ultimately most responsible for the development of our understanding of the real nature of heat phenomena and thermodynamics in terms of the motions of atoms and molecules, Ludwig Boltzmann. In a moment of despondency on September 5, 1906, when all others seemed to have rejected and ridiculed his life's work, he threw himself to his death from a tower in Vienna. Such were the passions. But the opponents of the atomic picture of matter were to lose. What had begun with Dalton's premise of different kinds of particles of matter for each element and of their combination in multiple proportions to produce new compound chemicals to explain the chemical properties of matter had been extended by Boltzmann to explain physical and thermodynamic properties of gases, liquids, and solids. By the turn of the century, it had all come down to one final contest. The last argument against the atomic hypothesis was simply that these atoms cannot be seen, can never be seen, and that therefore they are and will always be merely hypotheses. In 1905, Einstein published a theoretical description of Brownian motion. Brownian motion is a jerky motion of microscopic particles such as the black carbon particles in India ink that can be seen under a microscope to be in a perpetual dance, almost as though they were themselves alive. Einstein showed that this random motion could be understood and mathematically described as caused by the collisions of individual atoms and molecules with these tiny particles seen in the microscope. Hence, these particles enable us to see atoms. Between 1908 and 1911, Jean Perrin, working at the Sorbonne, bombarded the scientific community with brilliant experiments that verified Einstein's formula describing Brownian motion. Perrin marshaled a splendid array of evidence proving the existence of atoms, and in the words of Max Planck, its opponents gradually died out. Time passed them by and left them to sleep in history. What a short time the world would wait before these unseen things of hypothesis could shatter the world. No one says atoms do not exist anymore. A hidden power was unleashed from inside those hypothetical unseen things, and now no one sleeps so well anymore. The next section is called a connect the dot world. But what are these atoms? Incredibly, we now have atomic force microscopes and scanning tunneling microscopes that let us see and even manipulate individual atoms. But at the end of the 19th century, little was known beyond the fact that atoms must consist of pieces of charged matter. To explain that different materials, when heated to high temperatures, glow with different colored spectra, scientists proposed that atoms must have some kind of structure consisting of electrically charged parts. The structure was thought to look something like a marshmallow of positive electric charge with raisins of negative electrons stuck about the surface. In turn, these marshmallow atoms stuck to each other by the trillions upon trillions to form the objects of the world. But at the hands of Rutherford, even these ultimate pieces of matter shrank to a void. Substantial objects, such as tables and chairs, became mostly empty space. Everything about us, all the seemingly rigid, solid objects that make up our common sense world, we now know to be something quite different. Suddenly, scientists could look into matter and see it as it actually is, tiny specks in a vast void. You and I, tables and chairs, all specks lost in a void of space, held together by electric fields. We and all things we see about us are like a connected dot picture spread thin through space. As Rutherford peered with his beams of atomic particles into the atomic structure of matter, he found that the marshmallow atoms with raisin-like electrons stuck about them did not exist. Instead, his beam of particles zipped through matter as though nearly all of it were empty space. Unexpectedly, he discovered an intricate structure within the atom. He found that the mass of the atom resides in a nucleus of positive charge so small that if the atom were the size of a bedroom, the nucleus at the center would still be invisible to the eye except as a glint in a beam of sunlight. This more powerful probing of matter's structure revealed a new scientific material reality behind the illusions of solid matter. The probing revealed an atomic structure like a tiny solar system in each minute fleck of matter. And yet there was a flaw. These whizzing electrons, like tiny electric currents, should, in a flash of light, surrender all their energy and collapse everything into a millionth of its size. The electromagnetic theory of light, a crowning achievement of 19th century physics, demanded that these electrons radiate light and fall to the center of the atom, still and cold. But if they did so, the Earth itself would have collapsed long ago. There was a flaw somewhere, and as scientists at the turn of the century scrambled to fix it, other flaws in the great classical picture of reality began appearing. By the turn of the century, these flaws seemed to be everywhere. They signaled the great revolution in physics that has since altered our understanding of space, time, and matter. The next section is called Puzzling Light. At the turn of the century, two separate conceptual systems existed, one based on Newtonian mechanics with its ponderable matter, and the other based on Maxwell's equations. The equation was natural. Might not matter actually consist entirely of electric fields obeying and explained by Maxwell's equations, with Newtonian mechanics nothing but a summary of the electromagnetic laws of physics? Question. In this design, it would be possible to view everything as formed out of electromagnetic fields that act as stresses in this medium, this fluid that has to be there, filling all space for light to exist, just as ripples on a pond need water for their waves to exist. How close could Spinoza have dreamed we would come to realizing his idea of God than to have discovered that the substance of which everything consists is at once matter and, at the same time, the stuff that fills all space, the ether. Perhaps Albert Abraham Michelson, who designed the experiment to detect the ether as the Earth orbited through it, was too practical ever to have entertained such heady thoughts. Had I been doing that experiment, I could hardly have helped but think these things, think them, and then certainly say nothing of them. According to Maxwell's equations, light is a wave undulating, a fluid that fills all space and is called the ether. As the ether wiggles in its wave motion, the stresses that keep the undulation going give rise to the electric and magnetic fields we spoke of earlier. The Earth, in moving through space in its orbit, must move relative to this ether fluid. For example, when a light is turned on, the energy of the light begins to move through the ether as a wave that shakes the ether and travels with a speed characteristic of the stiffness of this ether. So if we measure the speed of light as it moves through the ether in the same direction as that in which the Earth moves with the ether or counter to the motion of the ether, and then again measure the speed of light crossing the ether perpendicular to the motion of the Earth, we should be able to see a difference in its speed measured in these two directions. By measuring differences in the speed of the waves of light sloshing through the ether, we should be able to determine the true motion of the Earth in space. That is, we should be able to see which way the Earth and Sun are moving off toward their endless destination in the night of space. But Michelson and his assistant Edward Morley found nothing. No matter which way they set up their apparatus to detect the smallest differences in the speed of light over different paths, they could not detect light undergoing any drag upon its progress that would give evidence of an ether fluid flowing with the Earth or across the path of the Earth in any direction. Maybe the Earth is stationary in the ether. No, the Earth moves in an orbit around the Sun at 30 kilometers per second. At some point along the Earth's orbit, it might be moving with the ether, but everywhere else it would have to be moving upstream, downstream, or across the ether stream. Still, Michelson and Morley found no motion. Perhaps the Earth drags along the ether immediately around it, like a wet sponge dragged through water. But this would result in easily observable consequences. Starlight would bend as it passed through from the outside of this ether to the ether being dragged along with the Earth. We would see the stars shift in the sky at different times of the year. These effects are not observed, so there must be another answer to this mystery of the ether. In 1892, an Irish physicist named George Francis Fitzgerald offered an outrageous explanation for the absence of any discernible motion through the ether. He reasoned that because all objects, including the Michelson-Morley apparatus, consist of matter held together by electric and magnetic fields, fields that are actually stresses in this ether, motion through the ether should distort these same fields just as much as this motion would affect the propagation of the electromagnetic waves. If so, then the ether's motion would also cause the atoms of the apparatus to bunch together. The light waves measured with those yardsticks would seem to travel farther in a given time than they actually did go and exactly compensate for the slower speed of light measured by Michelson and Morley. Shortly after Fitzgerald's proposal, the Dutch physicist Hendrik Antoon Lorentz independently reached the same conclusion and proposed equations to explain the effect. This contraction hypothesis became known as the Lorentz-Fitzgerald contraction. The equations are known as the Lorentz transformations. The difficulty, however, was that this solution seemed just a bit too pat. In 1905, Einstein had a better idea, an answer that has revolutionized our conception of space, time, matter, and energy. It is a picture in which space and time, matter, and energy are relative. They depend on the observer in a very curious way. The curious thing about the way the picture of reality has to be altered is that the space and time in which objects exist, the very basis of the idea of objective reality, must be made conditional upon the vantage point of the observer who looks upon this reality. For the first time in physics, we discover that these basic constructs of objective reality are contingent upon the conditions under which we observe space, time, matter, and energy. As a result, the theory of relativity gives us the first indication that the picture of an absolute objective reality is false and must be changed. Remember how the physicists at that time were looking for a way in which Maxwell's electromagnetic theory could explain all matter. For other physicists at that time, this suggested an underlying, all-pervasive ether that would account for the properties of the electric and magnetic fields. From this idea, perhaps a theory of matter as frozen chunks of electromagnetic stress in the ether, chunks of ether, might explain all the properties of matter. But for Einstein, Maxwell's equations were fundamental. Why try to explain them in terms of something else? Why concoct an ether? For Einstein, the question was not how does motion through the ether affect the propagation of light, but how should Maxwell's equation look to an observer traveling near the speed of light? As Einstein thought about this problem, he hit upon a very simple, unexpected answer. Perhaps Maxwell's equations are exactly the same for a moving observer as for a stationary observer. This is the way things work for ordinary Newtonian mechanics. In fact, it is an old principle in mechanics known as Galileo's principle of relativity. All the laws of mechanics that are valid in one frame of reference, such as fixed to the ground, will be found to work exactly the same way when tested in a uniformly moving, constant velocity frame of reference, such as in a smooth-traveling airliner. If you drop your pen while flying in a plane, it falls to the floor just the same as it would fall if you were sitting at your office desk. Think about it a moment. That is quite remarkable. The fact that you are zooming through the air at 500 miles per hour has no effect on the way the laws of mechanics look to you. Now, as Einstein saw the issue, if Maxwell's laws are to be so fundamental that they might replace classical mechanics, then surely Galileo's principle of relativity must apply to electromagnetic phenomena as well. There was just one problem with this idea. In Maxwell's theory, the velocity of light is a constant, always the same speed. It does not depend on anything. It does not depend on space or on how we move through space. And why should it? Space is nothing. If space is nothing and Maxwell's equations are absolutely correct, then the velocity of light must be constant under all conditions of uniform motion through space. Even when we move relative to the source of light with any velocity, the light always goes at the same speed. Even if we travel in the same direction as the light, at a speed almost as great as that of light itself, we must still find that it races ahead of us with the same speed. How could it be possible for light to travel at the same speed no matter how fast we travel? Whatever the answer to that, the Michelson-Morley experiment showed without a doubt that the velocity of light is a constant. Every observer, no matter what his or her speed, will find that light travels at the same speed relative to him or her. Ptolemy, Copernicus, the Greek sages, all the medieval theologians, and even modern astromancers had it wrong. The earth is not the center of the universe. You are, I am. But if we are going to get ridiculous results like that, if the speed of light must stay the same no matter how fast we move, then something else that comes into play when we measure the speed of light must be relative and not absolute. Thus, Einstein made the brilliant deduction that measurements of space and time, the things we measure in order to determine the speed of light, must be relative concepts, whereas the speed of light itself must be a constant and absolute. When Einstein calculated the changes in space and time that would be necessary so that all observers would measure the same speed for light, he found that all objects traveling through space must undergo a contraction. When we use our measuring rods to measure the length of objects moving very rapidly past us, we find that those objects are all shorter. But they are shorter not because of any ether causing them to contract, but because space itself contracts. Also, moving clocks run slower than our clocks, not because of any ether affecting their works, but because time itself runs slower for objects moving relative to us. The well-known twin paradox illustrates just how strange this is. One twin on his 20th birthday sets out from Earth aboard a rocket that will carry him at near the speed of light, say 90% the speed of light, or 165,000 miles each second. The other twin stays on Earth. Watching his twin in the rocket, the earthbound brother will see his twin moving and aging more slowly than he himself ages on Earth. After 40 years have passed, the 60-year-old man on Earth will greet his 37-year-old twin brother returning from his great voyage in space. Even stranger, had the rocket-bound twin watched his brother back on Earth while his rocket coasted along at a constant speed, he also would have seen his earthbound brother moving and aging more slowly than he. That's why it's called the twin paradox. Each twin sees the other aging more slowly than he, yet when they are reunited, the earthbound twin is older. The reason is that the twin in the rocket must change his speed in order to turn the rocket around for the return trip home. Despite the queer appearance of the twin paradox, this effect has been confirmed in many laboratory experiments. Indeed, J.C. Haffel and R.E. Keating demonstrated the effect in 1972 by flying clocks around the world. They said there seems to be little basis for further arguments about whether clocks will indicate the same time after a round trip, for we find that they do not. Appearances take on a reality we might not have expected. We could understand that our yardstick might look shorter to an observer whizzing past us, and that this traveler's yardstick might look shorter to us as well. We could see that clocks might seem to run slower. It is easy to acknowledge that appearances might change, But Einstein has shown us that reality itself is contingent on our vantage point. We see that this local, this personal meaning of time has a real impact on what happens in the objective world. Twin A is older than twin B. They look at each other and see an isolation greater than what mere distance had written across their faces. This is an isolation each of us has from everything else. We are separate, utterly separate. We do not even share the same space or time with others. But there is much more of a puzzle here. The most basic property that objects have in common is their mass, the stuff of their substance. We measure the mass of an object by taking some reference force, like the force of gravity that can be used to move it. We measure how long it takes the mass to increase its speed under the action of this force. That is, we measure its acceleration. If we keep the force the same and use different objects, we can use this measurement of acceleration to determine the mass of an object. Thus, the result we get when we measure an object's mass depends on how we measure space and time. Consequently, Einstein's discovery that space and time have meaning that is relative to the observer's measurements mean that mass is also contingent on these measurements. If we continue to apply this force, the object moves faster and faster. Assume now that we have taken an object and measured its mass by giving it a push. Now let us apply a force to accelerate the object to a very high speed. At this new speed, we make a new measurement of its mass. We observe what happens as the object flies past, and we figure out what its mass is. But because space and time are distorted for objects that are moving relative to us, distorted in such a way that the speed of light is always constant, the mass we obtain by this measurement is also distorted. The mass is greater now that the object has been accelerated to a higher velocity. Einstein showed that merely increasing the velocity of an object increases its substance. The increase in mass that Einstein calculated is directly proportional to the increase in the energy of the mass due to its higher velocity. Subsequent events, Hiroshima and Nagasaki among them, have amply proved the equivalence of mass and energy and have confirmed the validity of Einstein's conception of space and time as relative to the observer. This equivalence of mass and energy has become such a cliché that it is easy to lose sight of its bizarre meaning. In Einstein's equation relating mass and energy, we find that the mass, the very substance of an object, is actually energy. What is energy? It is simply a measure of a substance's position at the different times when we observe it. Note that through all these explanations, there is an undercurrent of implications all leading to the same place. The way things appear to us has become something of the substance of what they are. This process implies an unexpected connection between energy and mass. Objects are the very potential to move, or to take further liberties, objects are their motion. Motion in a space that is itself nothingness. The very answer begs the question, what is reality? Somehow this enormous triumph of probing the nature of matter has left us with more of a puzzle, more of an enigma than we ever had before. And yet, isn't this what we should have expected from the beginning? When we seek objective answers about the world in which our basic facts reduced to statements about the location of objects at various times, it is so surprising that the philosophic meaning we uncover has no more depth than that objects are these motions. Is it surprising to find that reality is in fact our observation of that reality? But why should objective reality have an existence that is at all relative to our observation of it? This relativity of mass, space, and time is the first scientific indication that physical reality depends in some way on the observer. In relativity, the vantage point from which we make an observation, a measurement, plays a role in the description of physical reality for the very reason that space as such has no substantive reality. It may seem that I am exaggerating the significance of measurement making and the role that observation plays. It might seem more appropriate simply to describe the way space and time are distorted under various conditions of measurement and let it go at that. But Einstein, in his original paper on relativity theory, titled On the Electrodynamics of Moving Bodies, shows us that measurement is fundamental. Any limitation that affects our ability to measure a physical quantity, and that persists no matter how we try to devise equipment for the measurement, not only represents a limit on us, but also shows a limitation that must exist when any two physical objects interact. This limitation on me as the observer is also a stricture on nature. If I cannot get at the physical quantity, no matter what physical tool I employ, then perhaps that physical quantity never takes part in any physical interaction. And if that is so, if it plays no more role in physical processes, it is not a part of physical reality. The conventional wisdom in physics has been to concentrate only on this latter fact, only on the implications as a stricture on nature. But our purpose is to understand the basic fabric of reality. As we will see later, the observer will play a much more important role in understanding reality. By emphasizing the importance of the observer that already is to be found in the theory of relativity, I am laying the basis for us to discover a much broader picture of reality that will unfold as we go along. I remember mostly the rain. I spent most of the day driving across Alabama through Andalusia, Greenville, Butler. The purple lace of wisteria draped through the bristly pines painted long, secluded avenues beneath the backdrop of the dark sky. Deeper in the woods, I could see white dottings of dogwood blossoms heralding the end of the short southern winter. Here and there, where the road cut through a rise in the landscape, the gallery of an orange clay bank would fill my view. Then suddenly the silver skeleton of a steel bridge reaching over the Tombigbee loomed and passed. I sped west into the rain, into the long, dark afternoon. I was going where she had finally gone. I was going to Jackson. The place lies in that ill-defined realm so many cities harbor that is neither town nor suburb, but something between, with a mix of fast foods, gas stations, vacant lots, boarded buildings, homes not quite poor, a church then, an iron fence edging maybe 100 acres that sloped away down a gentle hill. They take care of the place in a fashion. I am not sure what I had expected, only what I had hoped. Something more than a gravel road, something more than the tags identifying block numbers, something more than ragged grass, something more than just a place to leave the dead. They lie there now side by side, there on that hillside cemetery waiting the ages. There is a long marble slab on which two stone pillows mark their names. Maurice L. Zender on the first, Marilyn Ann Zender on the second. Beneath these dates, 1899 to 1947 under his name, 1936 to 1952 under hers. She lies there beside the father I so often heard her say had died too young, the father she had loved so much. She lies there now in the place she had told me she would someday lie beside her father beneath the soil of Jackson. It was 5 in the afternoon when I got there. The rain had slackened to occasional showers. I found the grave. Eventually, it was odd. There was no sense of the time. So many, many years, and yet it could have been, oh, just a few days, a few months. I am not sure what I had expected. On the way, I wondered what I might find. Leaving, I guess, one always wonders what was found. It does not matter. We find only one thing: emptiness. Emptiness, that cloth that covers the ages of disappointment, that cloth that is never expected, despite the fact that it was always the only option. Just earth, marble slabs here and there, marble slabs scattered over the ground almost in some order, and the cedar bushes standing by twos about the hillside. It is a cemetery. It is a place where the dead do nothing. It is a place where the living come to learn that lesson once again. I stood there, believing I was fulfilling some obligation. The rain did not care. I stood there in wonder at all the time that had gone by, feeling wet, looking at the gray sky, and what? Wishing that there might be something more, wishing that this time, for this visit, there might be some bit of a miracle, some whisper, a whisper in my head, something. But she was not there. If she had any existence at all, she was not there. I left. I drove east into the night, into a pouring, weeping rain, into the black night. So much we will never know, so much more we have known that is gone. Fragments of life, of consciousness, the pieces of our having been here at all, of having lived. Those pieces of her life, as lovely and wonderful as she was, have all left only such fragments as these, and the rest of her has slipped away into eternity. End of chapter 3.